All right, let's go ahead and get started. One thing I want to clear up a couple of things. Just kind of housekeeping stuff before we get going. If you haven't already seen it, first quiz is up on Canvas under assignments. You just see a PDF. So I'm just going to kind of restate the announcement that I gave. The word quiz, I think, has certain implications to all of us, but these are, do this on your own time. It's not really time sensitive. I mean, it's due Monday, but really, yeah, we're not going to do these in class. You can use whatever resources you want. You can talk to other people. What I'm looking for is for you to show your arguments, show your work, and get practice doing that, since the homework doesn't really allow for that very well. So yeah, this is due on Monday, either a hard copy or you can submit it and upload it to Canvas, but yeah, it's up now. Has anybody had a problem finding this? Okay, good. Any more questions about that? Did you all see my office hours finally got assigned? Okay. Just to be really clear, I don't have office hours today. They're opening up that center on Monday. But as always, you can make an appointment with me if you need anything at all. And I think that was all I wanted to say about that stuff. So we're going to continue section 1.5 about continuity. Anybody have any questions about anything before we continue? Okay. All right, so we'll talk about this example last time. There's a discontinuity where x equals 0 because the limit does not agree with where the function is defined. Or actually because the limit doesn't even exist. So we didn't even need to compare them against each other. So let's look at this one now. Where is this function discontinuous? So I heard someone say at 3. Keep in mind that when we ask where a function is discontinuous, we are looking at x values. So we're looking at the independent variable. Okay. So do we know for sure that it's discontinuous at x equals 2? How do we know that for sure? Okay. So we're divided by 0. So we definitely know that, I can't plug 2 into this top definition of the function. Maybe we should answer this second question first. Where is this function defined? Everywhere. Because yes, you're correct in that first expression. I cannot evaluate where x equals 2, but I do have a contingency for that. So sounds like I'm not getting a lot of pushback on this x equals 2. Is it possible for this function to be continuous at x equals 2? What would have to happen? Okay, so let's investigate this limit. So how can we figure out what this limit is equal to? So the limit as x approaches 2, x squared minus x minus 2 over 3, or over x minus 2. We talked about a couple of techniques we could take advantage of last time. Will any of those work? Go ahead. Yeah, the numerator factors into what pair of factors? X minus 2, x plus 1 over x minus 2. Can I just plug 2 into this now? Yep. Because that's a polynomial. So this limit's equal to 3, right? So now where is this function discontinuous? Go ahead. Yeah. Oh yeah, I guess we all just assumed that. Oh no, so where is this function discontinuous? So why is 2 the only place we're looking? Okay, so Why are there any other points we have to look at for where it might be discontinuous? Why not? Okay. Right. So basically, we're looking at a rational function here. So the only way that might be discontinuous is if the function is not defined. And in other words, if the denominator is equal to 0. So as long as x is not equal to 2, I know this thing's continuous. So the only place we really have to double check is where x equals 2. But we have shown this. We have this limit 3 is equal to f of 2. So f is continuous at x equals 2. So this did not work out. So this function is continuous, or sorry, where's it discontinuous then? Nowhere. And moral of the story there is, I mean, you see a piecewise function, and most of the time, or a lot of the time, that'll mean that there's a discontinuity where that definition changes, but maybe there's not. Any questions there? Okay. All right, this function right here, has anyone ever seen this notation? So this is called the floor function. And I'll graph this and kind of describe what's going on here. Basically, what the floor function does is you can give it any real number, and it returns to you the largest integer. The largest integer that's still less than or equal to that number. So I'll give you a few examples here. F of 2.5 is equal to 2. F of pi is equal to 3. F of 10 is equal to 10. So basically, kind of the informal way to say it, if you have something that's not a whole number, it'll just truncate all the decimal stuff. It'll just get rid of it. So basically, if I were to graph this function, it would look like this. You have these levels that would jump up every integer. Question? So do we understand how this function works? Where is it discontinuous? Is it continuous at 2.5? Gotta vote for yes. So let's figure out where 2.5 is here. So 0 to 1, 1 to 2. Right here, this would be the point 2.52. What's the limit as x approaches 2.5 from the left there? What's the limit as x approaches 2.5 from the right? What is f of 2.5? Okay, so that's continuous at 2.5. I could also argue that it's continuous at pi, because this point right here is pi 3. Is it continuous at 10? No. So can we generalize it a little bit? We know we're continuous at these two places, but not at x equals 10. Where are the discontinuities on this thing going to be? All the integers. Where's it defined though? Everywhere. This symbol also means integers. You'll see that from time to time. So this function you won't. It's a good thing to look at when you're talking about continuity. Any questions on this guy here? This is the floor function. There's also a ceiling function, which acts the exact opposite way, and it's very similar. All right, so talk about continuity. We talked about 1 and 2 set of limits. Now we can talk about continuity in the same way. So let's say I have a function f, and I'm saying it's continuous from the right at some point a. Basically, that is directly tied to that one-sided limit. So just to kind of back up, all continuity is, actually, so I'll ask one of you, what is the definition of continuity? If I say a function is continuous at a point, right? And when you say limit there, if you don't specify what you mean by limit, you mean two-sided. So this is kind of the one-sided analog of that. If I say a function is continuous from the right, then the limit as I approach from the right is equal to the function there. Pretty clear idea, or pretty similar idea from the left as well. So sometimes we will not be asking about the continuity of the function. We'll be asking if it's right continuous or left continuous. Or I'm wording it continuous from the right or continuous from the left. All right, so let's apply this to the weird function we just looked at. So we already said that this thing is discontinuous at all integers. Well, let's talk about this. Where is it right continuous? Is it still going to be everywhere but the integers, or can we add some more things to that set? Right continuous everywhere. So let's look at, for example, let's just look at x equals 1. What's the limit as x approaches 1 from the right? What's the that limit? Well, that limit is 1, right? Is the function equal to 1? Yeah. So I think it's right continuous everywhere. Go ahead. Yeah. And really, the way you'll hear this most worded is, I'll abbreviate, continuous from the right. And yeah, that again means this. The limit as x approaches a from the right of f of x equals f of a. So it's right continuous at all places. How about where it's left continuous? And again, we can look at, obviously every integer, like if you were to break this down into, 1 unit wide intervals, they're all going to have the same. Is this left continuous at x equals 1? Why not? Right, so for example, the limit as x approaches 1 from the left is equal to 0, which is not equal to f of 1, which is 1. So it's right continuous everywhere. Where is it left continuous? Yep. So everywhere except the integers. And just to kind of show you how all these things kind of feed together, if I tell you a function is continuous at a point, let's just say, without being specific about what I mean by continuous, what can you tell me about the one-sided continuity on either side? Let me write out what I said because I don't think I think I tripped over it. Let's say f is continuous out x equals 4. Is it continuous from the left at x equals 4? Want to vote for no? Anybody else? If I tell you a function is continuous at a number, it's continuous from both sides. So think about when we talked about limits. If I then the one side. In fact, why don't I erase? Because I did not mean for this at 4 to be tied to this specific function. Let me just go to a new slide. So before we get into this thing, actually, this is probably a good place to talk about the definition. I'll just say this is a third bullet. If f is right and left continuous at x equals a, f is continuous at x equals a. So again, just like an analog to back to the first time we talked about limits. If your limit from the left and your limit from the right agree, then the two-sided limit is that value they agree on. So in this case, let's say that both these first two bullets are both true. If the limit as x approaches a from the right is f of a, and the limit as x approaches a from the left is f of a, then can I say this for sure? Yeah, that's absolutely true. Well, that's a consequence of the two one-sided limits being what they are. Any more questions about that? I think that was a good thing to really unpack. And this one here, I don't think we need to go through this one in real detail, but I do want to talk about this language, continuous on the interval. Because so far, everything we've talked about is we've examined points, right? Is this function continuous at x equals whatever? We've just talked about continuity at one location. So if I'm saying this here is continuous on the interval, -1 to 1, what that means is this. F is continuous at every point. Inside this interval, -1 to 1. I think I'm going to leave this. If we have time, we'll come back to it. But Maybe there's some more important things we can cover. In either case, I'll kind of write this out on the notes, but I do want to explain why guarantee this. But for us to go on, I wanted to be really clear about what that phrase continuous on the interval means, because you're going to see it a lot. Kind of like with that floor function, we said it was continuous everywhere except for the integers. We specified a set there of all the points where that function is continuous. All right, so as I said, continuity is really just an application of limits. I gave you a bunch of limit laws and we talked about them earlier this week. So here's some corresponding continuity theorems. So if you have two functions, f and g, that are continuous at a point A, then all of these things are continuous as well. A sum, a difference, any constant multiple, their product, quotient, f over g, provided what? That what? G isn't zero where? Really, I'm only looking at continuity at one point again. So G can be zero sometimes, but where do I really want it to be non-zero? At A. So remember right now, I'm not guaranteeing anything about where else is continuous, just A. And this one's a little more mysterious. F composed with G. So that is continuous, but there's one thing you got to watch out for. So that value A, what function is that an input to? G. And then when you're composing functions, what's the corresponding input going to be to F? G of A. So I need F is continuous at G of A. Just basically got to make sure that your function is not going to be broken by, or your function F is not going to be broken by G of A. But just like the limit laws, these give you a few more approaches you can use if you're looking at a function that's pretty complicated, you can break it down into its smaller pieces and handle them one at a time. Any questions before I move on? All right, and something I've alluded to a lot, but here's something you can definitely guarantee all the time. Any polynomial function is continuous everywhere. So remember what polynomials look like. Basically, they all take this form. Call it P of X equals, A0 plus A1X plus A2X squared plus whatever, as many terms as I want, so long as it's a finite number of them. So basically, it's just non-negative powers of X, and I'm multiplying and adding all those terms together. There's no real way that can be undefined. There's no way that can be discontinuous. So any polynomial is continuous everywhere. Any rational function is continuous everywhere. What's supposed to go in that blank there? Remember, let's say a rational function looks like this. So it's polynomial in the numerator, and it's a polynomial in the denominator. I think I have a right. So everywhere that the denominator is non-zero. There's one more on the slide. This is also true for radical functions and trig functions. So trig functions, sine and cosine, you probably picture those graphs in your head. They're continuous absolutely everywhere. Tangent, I cannot say the tangent function is continuous everywhere because it has places where it's not even defined, but everywhere where it is defined is continuous. Radical functions like the one we kind of just glossed over, that one is also continuous everywhere where it's defined. Okay. So let's look at an example here. I want to find this limit as x approaches -2 of this thing here. How might I do that? How would I find that limit? Go ahead. Okay, so I got one proposition for this. Let's just find f of -2. What allows us to do that? Go ahead. Right, so what kind of function is this? So this rational function is continuous at x equals -2. Now, this is probably the most efficient way I can say this, because f of -2 exists. As long as the rational function is defined, I know it's continuous there. And since I know it's continuous there, I know the limit has to equal whatever happens when I evaluate the function there. So f of -2, what happens when I plug it in there? I get -8 plus 8 minus 1 over 11. That limit is -1 over 11. Unless someone finds an error, which is possible. All right. So I got three different functions here. I want to find the intervals that each of these following functions are continuous on. How about f? Where's that one continuous? Everywhere. Why? Polynomial. So all real numbers, -infinity to infinity, however you prefer to say that. Polynomials are easy. We very well understand how they behave. How about g? Where is it continuous? And I'll start by saying this. Let's just say the real numbers except for. Got to vote for -1. I got to vote for 1. Because x squared minus 1 equals 0 implies x equals -1. Any other places where that one might not be defined? Are you happy with this notation, or is it kind of throwing anybody? I'm guessing this might be a little more familiar to people. And this is one of those, I have no preference for how you express those, whichever way makes the most sense to you, you're fine. I'm happy with. And yeah.
Just the middle part, the -1 to 1. Does that include that?
No, the parentheses mean that I don't. So yeah, anything between -1 and 1 is continuous for.
Oh.
Yeah, so it's simple. It is only the values negative. Or that. Yeah. Yeah. So yeah, that's not an ordered pair or anything. That's so, and just kind of a notation thing. Curly brackets mean -1 and 1, just those two things. The parentheses mean everything fixed, everything between them, without including the ends. And finally, H. Where is H continuous? Okay, I got one vote for every place except 1. And I think that comes from the middle. The middle one's clearly undefined at 1. Yeah, negative numbers are going to be a problem too, right? Why is that? Right. So because of this, and in fact, let's just kind of break down each one of them. This one right here is going to be continuous only for this set of numbers, the non-negative numbers. This one here is going to be, I'll say it like this, all but x equals 1. And how about the third one? Where's that one going to be discontinuous? Be careful. Yeah, that one is continuous everywhere. We're limiting ourselves to the real numbers, so I can't make that denominator 0. So this one right here is all real numbers. So then when you're thinking about where this is going to be continuous, basically you have to, if any one part of this has a discontinuity, then the sum of all three of them does. So what's my final interval or my final set of numbers for where this one's continuous? Go ahead. Yeah. Yep. So I am just talking about this third term here. So that's a rational function, right? So rational functions are continuous except when the denominator is 0. And yep. So I think if I'm going to put together a final interval for this, I think it's going to be this. From 0 to 1. And from 1 to infinity.
Notation on writing domain.
Not at all. So yeah, I mean, as long as it's clear. So any of the things I've written here are fine. I'm only showing them multiple ways, just give you as many looks at it as I can. All right. And 2 more here. Where are these functions continuous? So as we're looking at the first one, if you look at it as sine of x squared, that might be a little difficult to think about, but what you can do is, you can think about it like this: f composed with g, where f of x equals sine of x. and g of x equals x squared. Where is x squared continuous? Where is sine of x continuous? So where is their composition continuous? Absolutely everywhere. And if another kind of informal way to look at it is, all right, I'm starting with x. Is there a number that can't be, is there a number I can't square? Like if I square it, it'll give me back undefined. No, that doesn't exist. Is there a number I can't take the sine of? Either one of those things is going to ever fail you. So this is continuous everywhere. Capital F here is a little strange. What kind of function am I looking at here? Is it a rational function? Technically, no. You can see that you might be able to compose it in such a way that there's a rational function that's a piece of it, but it's not, strictly speaking, a rational function. Let's see a radical function in there. But here's the bottom line. I see a rational function composed of a radical function. And those are two of the types of functions that you can that are guaranteed that if they're defined, they're continuous. And I can say the same thing about their composition. So really what I'm asking here is, where is f defined? Yeah, I got one vote for this, everywhere except -3 and 3. Okay, so those will definitely give you a division by 0. Oh, we don't know. So that was a suggestion someone gave and put back to you. Here's basically whether or not this was done explicitly. This is probably the equation that was solved. I want to know what's going to make my denominator equal to 0. So clearly -3 and 3 will make it, we're going to make this discontinuous. Anything else? Which function? The whole, it can be negative. I think, like, for example, if you have x equals 0, the output of the function will be negative. But I think, oh, sorry, you're probably talking about the square root. Is it possible for that square root to be negative? No. And to make that clear, let's say I want to find where x squared plus 7 is less than 0. So that means x squared would have to be less than -7, which that can't happen. So I agree with this. The only two values in all the real numbers that are going to, where this is going to be discontinuous, is -3 and 3. We agree with that? All right. So next theorem we're going to talk about, I want to get us thinking about it. So if I have a function that has these properties, it's continuous on the interval from 0 to 4, including 0 and 4. F of 0 is equal to 1, f of 4 is equal to 6. Answer these following things with true, false, or maybe. Is there some x value on that interval where the function is equal to 5? I heard some mostly trues, I think. Is there some c on the interval where f of c is equal to -2? Got some no's, got some maybes. Sounds like the maybe is narrowly 1. And for some C on the interval, f of C is equal to 1. I got a true and I got a maybe now. Yeah, absolutely. So, for example, this top interval, 0 is on. Does that clarity make us change our vote on that bottom one? To what? Okay. So this is a theorem maybe you've seen before, but it's a pretty important one in calculus, the intermediate value theorem. So now let's generalize the kind of the suppositions I just gave you. If I have a function that's continuous on some closed interval, when you say closed, I mean it contains the endpoints. F of A is not equal to F of B. Let capital N be any real number that's strictly between them. Or in other words, one of these two things is true. And the following is true. There's a real number on the open interval such that f of C equals N. Sorry. So let me, while you all are writing, I'm going to go ahead and illustrate the thing I just talked about. I may have to go back and remind myself of the numbers, but I think it was, my function is continuous from 0 to 4, right? F of 0 was 1, and f of 4 was 6. There are my 2 points, and I have no idea what the middle of the function does. I know that it's continuous, but I don't know really anything more than that about how it behaves in between 0 and 4. And the levels I had were 5, -2. Let's ignore the fact that it's not to scale at all. And the last one was it 1? And I think 5 is probably the most clear. I know that somewhere between x equals 0 and x equals 4, I have to get from y equals 1 to y equals 6. And there, now if I take the word continuous out of this, then obviously you can avoid y equals 5. But no matter what this function does, it's going to have to cross y equals 5. And you all said that maybe for -2, right? So yeah, because I don't know how this function behaves in between those 2 points, then yeah, it very well could have got to -2, but it's not guaranteed. Why was the answer maybe when I gave you the value of 1? Right. Yeah. Easiest example I can give you is if it was a straight line between those 2 points, then nowhere on the interval, on the open interval, did I ever reach 0 or 6. On the closed interval, I reached both, but that's not what the intermediate value theorem gives me. This theorem gives me something about what happens on the open interval, so without using the endpoints. Any questions about that? That's why I put the value of 1 on the last slide. So yeah, so it sorry. When I say strictly between, I mean it cannot even equal one of the two endpoints. Yeah.
Gotcha.
So, and I'll clarify these by saying this: less than and not equal.
I see.
Mhm. All right, this guy here, f of x. Does this have a root on the interval 1, 2? What does it mean when a function or what does it mean for a function to have a root? Like if I said, all right, this function has a root at x equals 9. What does that mean about f of 9?
That's basically-
It's the x-intercept. So it's where the function equals 0. So basically I'm asking this. Does f of x equal 0 on that interval? So let's use the intermediate value theorem, and I gotta fast forward a little bit. So what's the first question I have to ask myself? Is f continuous on this interval, the closed interval from 1 to 2? Okay, I got some votes for yes. How come? Continuous everywhere because polynomial. All right. Next thing I should probably look at is this. What is f of 1? -1. What is f of 2? 12. Is that enough? Okay. So because f of 1 is -1, and because f of 2 is 12, and this is kind of obvious, but I'll say it anyway, because -1 is less than 0, which is less than 12, is this a symbol you all are familiar with? Means therefore. I don't know why. Therefore, f of c equals 0 for some value c. Like this, for some value c that's right in between 1 and 2. So because I got a continuous function on a closed interval 1, 2, and really it's a polynomial, I could have took any interval I wanted. I know that at either endpoint, the function has different signs. You got a negative at the left and a positive at the right, which means that somewhere in between them, the function must equal 0. I'm not telling you anything about where it is, but there must be a place where that's true. Any questions? All right, that is all for 1.5, and that's all for this week. I'll stick around if anybody has any questions. When I get home, I'll update due dates and all that stuff, but have a good weekend all. See you Monday.